Hi everybody, welcome back. This is Earth and Space Science 102. I'm Stephanie Welch, and this is lecture 22. This is part 2 of the life stages of a star and the life story of a star, except today we're covering high mass stars. So this is one of my very, very favorite subjects to talk about in the entire semester. And if I can't awe you with the kind of processes that go on in a high mass star and the fusion of heavy elements that ultimately form a planet like our own, then I'm not doing my job right. So we're going to start essentially the same way that we started with low mass stars. I'm going to give you a little bit of an outline to go over, give you an idea of how the star's lifetime is going to ultimately break down. And really it's going to be very similar, especially in the initial stages, to a low mass star like our sun. The difference in a high mass star is going to come into the rate in which fusion takes place, the overall main sequence lifespan of a high mass star, the post-main sequence lifespan, and the advanced fusion of heavier elements, and how a star that is a higher mass star than our sun will ultimately end, and what kind of amazing death throes it has in store. So stage 1, step 1 of a high mass star is going to be incredibly, very, very similar to the first stage of a low mass star, so much so that we're going to kind of speed through that pretty rapidly. The only real difference in this first step, where the star actually forms, is that a higher mass star is going to require the collapse of more gas, a bigger nebula, a denser patch of the universe all collapsing down to form a single star. Because in order to form a high mass star, you need potentially hundreds or even thousands of times the mass of a star like our sun. So you just need more matter there collapsing down to one place to form a star that would be considered a high mass star. And once it forms, it's going to initially start doing everything that a low mass star would do. All stars are going to start with hydrogen fusion, and hydrogen fusion is going to be the equivalent of the main sequence lifespan of that star, or step 2. Now, the main sequence lifespan with a high mass star is going to be quite a bit shorter than its equivalent low mass star, because it's fuel inefficient, because it's burning through that fuel incredibly fast. So after a mere 5 million years, not even enough time to allow for the evolution of life on any of the planets surrounding that potential star, the main sequence lifespan is gone, and then you enter into these amazing death throes. Step 3, the post-main sequence lifespan, where you're creating all of these heavier elements. We'll call that the supergiant phases. And then finally, when fusion can no longer continue, and we'll establish the point in which fusion can no longer continue a little bit later on, then the star explodes in this amazingly rich experience called a supernova, creates a gigantic leftover gas cloud called a supernova remnant, and the collapse of the core generates either a neutron star or a black hole. It depends on how much mass is there. So let's start at step 1. Let's start from the very beginning here, where we have this gas cloud. You just need more matter. It's a matter of matter. You need more mass. You need a thicker, denser, more abundant gas cloud, perhaps light years across, many, many light years across, to all collapse down to form a single star in order to have a star that's more massive than a star like ours. And if you can do this, then you can generate a high mass star. So that's the first of 2 stages that are very similar between the low mass star and a high mass star, just a matter of having more mass there to create the high mass star. The second stage that's ultimately very similar is the main sequence part of the star's lifespan, because what's ultimately happening, even though it's happening in a different way, is that hydrogen is being converted into helium. So we'll kind of just blow through step 1 here, assuming that the process is very, very similar to a low mass star. Gravitational collapse converts gravitational potential energy into thermal energy, crushes this material inward and inward and inward until you have high enough core temperatures for the onset of fusion. Once that happens, the star is in balance for as long as hydrogen fusion can continue, and you enter into step 2, the relatively short in comparison main sequence lifespan of a high-mass star, when hydrogen fusion will take place. So hydrogen fusion within the core of the star is the main sequence lifetime. And even high mass, high temperature stars like an O, B, or an A-type star will have these core temperatures that are initially going to be conducive to going through this hydrogen fusion. You also have to think about it in a sense of there being very few other types of fusion that are going to be possible because heavier elements are going to be relatively rare, at least initially in a star's lifespan. Most of the universe is hydrogen. The second most abundant element in the universe is helium, and together those make up 98% of the universe. So in order to build everything else, carbon, nitrogen, oxygen, iron, silicon, all of these other elements, we need the kind of high temperatures that happen in the post-main sequence lifespan of a high-mass star. So even hydrogen fusion, the main sequence lifetime, and then the post-main sequence lifetime of the helium fusion taking place to form stuff like carbon and oxygen, those are still going to be relatively similar to the low-mass stars that we already talked about. So to lay all this out on the periodic table, which I'm going to do sort of intermittently because you might not be as familiar, you might not spend as much time with the periodic table as I do. Let's kind of lay all this out and see what we've created so far and what we will create. There are 114 elements that have been stabilized, 92 that are naturally occurring, and we think that all of these elements have to be created in stars, whether it's through fusion reactions or in the supernova explosion, ripping apart individual atoms so they come back together again as weirder, denser versions. All of these elements are going to be created in stars. First, through converting hydrogen into helium, which is what a low-mass star can do as well, through the proton-proton chain, and high-mass stars are simply going to do this through the CNO cycle. So while low-mass stars convert hydrogen into helium, helium into carbon, and maybe some oxygen, and that's about it, the high-mass stars are going to go on to create virtually everything else. Now, the main sequence lifespan of a star, like a high-mass star, will be relatively short because that star is going to use carbon, nitrogen, and oxygen as catalysts in the reaction, and that's why they're, in a sense, so fuel inefficient while they burn through all that core hydrogen rather quickly. Because using these heavier elements as catalysts in the reaction can make this happen at thousands and thousands of times the rate in which fusion happens in a low-mass star. So in order to get hydrogen and multiple hydrogen atoms to be converted into helium, what you're essentially doing with using carbon, nitrogen, and oxygen is just continuing to add a proton along the way, continuing to add a whole hydrogen atom, bumping up the atomic mass until you end up with something that is conducive to sort of spitting out a helium nucleus. And in this way, you're converting hydrogen into helium, but along the way, as a side effect of this process, you're converting carbon into nitrogen, nitrogen into oxygen. So that's the CNO cycle. That's effectively how a high-mass star undergoes a relatively short main sequence lifespan and converts hydrogen into helium. Now, as we move beyond that, we see carbon is converted into nitrogen, nitrogen is converted into oxygen. So you're already, even in the main sequence lifetime, going on to produce some of the heavier elements that we need on Earth, that the rest of the universe is going to be composed of, even though it's in relatively small abundance. Now, as a reminder, these high-mass stars are going to have a very, very short lifespan that is a fraction of 1% of the lifespan of a low-mass star. A low-mass star with a lifespan of 10 billion years is 2,000 1,000 times longer of a lifespan than a high mass star that might only be undergoing hydrogen fusion for a mere maybe 5 million years. And then all of these post-main sequence steps that we're going to talk about in the formation of all these even heavier elements are going to happen really, really rapidly. So the high mass stars are around for a short period of time. They go on to do these incredible things, and then they die really, really, really young, in a sense, that they do everything that they need to do in a much shorter period of time than the low mass stars, sort of stretching out their existence for a longer period of time. Now, in order to go through the fusion of all of these heavier elements and to build everything else on the periodic table, you need subsequently higher and higher and higher temperatures. And this table does a really, really good job of showing you what kind of temperatures are required to go through all of these higher and higher and higher forms of fusion. So to take hydrogen and convert it into helium, you don't really need core temperatures that are that high. In a massive star, you need core temperatures at a minimum of about 5 million Kelvin. That's really, really high compared to anything naturally happening on Earth, but not so much compared to the kind of core temperatures that can be reached in a high mass star. To go on to convert helium into carbon, that's another thing that even low mass stars can do, you need temperatures in excess of 100 million Kelvin. And that happens for a relatively short period of time, hundreds of thousands of years as opposed to millions of years. Then to go on to convert carbon and helium into oxygen, carbon into neon, neon into magnesium, and build heavier and heavier and heavier elements, ultimately getting up to this point of forming something as heavy as iron, you need temperatures first in the hundreds of million Kelvin to the billions, and to reach this highest form of fusion that's actually possible in the core of a star, to actually form iron, you need core temperatures in excess of 2.5 billion Kelvin. This is a kind of temperature that's not naturally occurring anywhere else in the universe, but the very, very highest mass O-type stars are capable of reaching these core temperatures. And the proof is that on Earth, we have material that's composed of iron and silicon and sulfur and all of these heavy elements. And we know that these heavy elements were not formed in a star like our sun. These heavy elements could only have been formed in the first generation of stars in the universe, in these high mass stars. So let's just take a second before we look at the mechanics of all of this and this process of taking carbon and turning it into neon and turning it into all of these heavier elements. Let's take a moment to just truly stop and appreciate this, because this is one of the most amazing things that modern astronomy can really tell us, and one of the most amazing things that astronomy can bring to us is that our entire planet, composed primarily of heavy elements, are heavy elements that are found in a relatively small abundance in the universe. And in order for those elements to have been formed in the first place, they had to have been formed in high mass stars. So initially in the universe, you had these high mass stars churning out all of these heavier elements, churning out all the silicon and oxygen and iron that are incredibly abundant, not just in the Earth itself, but even the heavy elements that are abundant in our own bodies. The carbon in our bodies, all of even maybe the heavier elements that are found in smaller abundances. We even have some amount of iron in our bodies. Everything that makes up you and everything else that you see in nature and everything that makes up our world was once formed in a high mass star. Carl Sagan put this really succinctly as, we are star stuff. We are made of the same elements that were originally created in stars, and that ties us back into the universe. Neil deGrasse Tyson put this in a way that's just absolutely beautiful to me, and I hope you appreciate it too. He called this the most astounding fact that astronomy could bring to us. So I'm going to play you a little short clip where he's doing an interview with Time magazine, and he's talking about this idea of forming heavy elements of stars as being the most astounding fact. And I hope you find it as beautiful as I did.
What is the most astounding fact you can share with us about the universe?
The most astounding fact.
The most astounding fact.
Is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high-mass ones among them, went unstable in their later years. They collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us. When I reflect on that fact, I look up. Many people feel small because they're small and the universe is big, but I feel big because my atoms came from those stars. There's a level of connectivity. That's really what you want in life. You want to feel connected. You want to feel relevant. You want to feel like you're a participant in the goings-on of activities and events around you. That's precisely what we are, just by being alive.
All right, so the most astounding fact. That was always just so incredibly beautiful and moving to me. Now let's look at the mechanics of how that actually works, how you create iron and silicon and sulfur, all these progressively heavier and heavier elements, with the knowledge that you have to have higher and higher core temperatures in order to make that possible. And those core temperatures will only be reached in progressively higher and higher and higher mass stars. The kind of stars that were incredibly abundant in the universe originally, when it was small and dense, but now that the universe has expanded outwards, they are relatively few and far between. The first thing that's going to happen is that finally we have core temperatures that are going to be high enough to undergo fusion involving carbon and oxygen and neon. And so what you can continue to do is take these elements that you already have in the core of a star and start to fuse helium nuclei to it. Add a mass of 4 every time you fuse another helium nuclei to it. So carbon plus helium effectively creates oxygen. Oxygen plus helium effectively creates neon. Neon plus helium effectively creates magnesium, and on and on and on down the line. And you can build up to a certain point just by continuing to do the math of adding these helium nuclei to whatever it is that you've already created. So you already need incredibly high temperatures in the excess of hundreds of millions of Kelvin to be able to do that. With some of these stars that we're considering to be high mass stars, they might get to this point and we might consider them to be a high mass star, but this might be the end of the line. They don't have core temperatures to go on beyond this point, and so their core will collapse, the outer layers will be shed outwards, and that will be the end of their life. Only the highest mass stars, the ones that are practically non-existent today, are capable of going beyond this step of taking carbon, turning it into oxygen, neon, magnesium, and so on. Only the very highest mass stars will get us all the way up to the point of forming iron. The heaviest elements will only be created when you have the kind of core temperatures up in the billions of Kelvin. So that's when you actually have to take whole carbon nuclei and attach them to other atoms and continue to build. So what you're doing is, instead of adding a mere mass of 4 every time, you're adding a mass of 12 every time. And you can significantly wrap up your atomic mass and subsequently your number of protons, what element you're actually dealing with. So by adding oxygen to carbon, you create silicon. Silicon is the second most abundant element in the Earth's crust. So we're standing on this planet that's incredibly abundant in silicon, something that can only be produced in stars that are practically non-existent today. But they were much, much more prolific in the past in the universe. So carbon plus oxygen creates silicon. 2 oxygen atoms together create something with a mass of 31. Once you kick out a neutron, it creates sulfur. 2 silicon atoms effectively create iron. Iron is the most abundant element in the Earth's core and the core of all of the rest of the terrestrial planets. Our planet wouldn't be able to create a magnetic field without the iron present in the core. That is the last step in the advanced fusion reactions of these highest mass stars. So while relatively rare today, these processes are incredibly important for the formation of all of these heavy elements that ultimately make up our world and our bodies. So that's where we're getting to. And when you take a look at this on the periodic table, the next obvious question should be, but that only gets us to atomic number 26. We have to get all the way up to 92. What happened to the entire rest of the periodic table if that's the end of fusion? That is going to be the end in terms of fusion, in terms of what a star is capable of producing in the normal part of its lifespan. But that's not the end in terms of what a star is capable of producing in its death throes. This grand production of death in a high mass star, it's called a supernova, is going to be capable of essentially producing everything else on the periodic table, and possibly more, possibly stuff that isn't found on our planet, at least in any kind of major abundance, and therefore is relatively unknown to us still. So we get up to this point of forming iron, and if you look at all of those elements that are built up to the point of forming iron, they're pretty common on Earth, and we think they're pretty common amongst all the rest of the planets in our solar system and other systems. When you go beyond the point of iron, you see that everything else on the periodic table is really rare. Stuff that you don't really hear of too much. Osmium, gold, uranium, iodine, all of these sort of bizarre, relatively rare elements that definitely don't make up the majority of Earth or Earth's biology in any sense. The reason why they are rare is because it takes not the normal processes of a star, but the death throes of the star to produce those elements. Now, if we take a step back for a second, because we haven't quite gotten to that point of looking at the star's ultimate death yet, we haven't gotten quite to the point of creating that supernova, let's look at the highest mass star possible right at the very, very end of its life. Once these core temperatures are built up because of the contraction of the core and the expansion of the rest of the star, then it's going to be capable of producing all of these subsequently heavier and heavier elements up to the point of forming iron. And what you ultimately get are all of these advanced forms of fusion all taking place at the same time in a star. An O-type star, a very, very high mass star, is capable of producing iron at the same time that it's producing carbon and nitrogen and even helium. All of these things are taking place in a series of nested bands, nested shells around the very, very core. And wherever you have the highest temperatures, that's going to be the very, very center core, and that's where you're going to form the heaviest elements. So iron is going to build up in the very, very, very center core of a star, and right around that iron, you might have a little bit less massive of an element. You might have a buildup of silicon, and then sulfur, and then subsequently lighter and lighter and lighter until you get all the way up to the surface. We have carbon and then finally helium produced. So you have these nested shells of subsequently heavier and heavier elements as you go in, lighter and lighter elements as you go from inwards out. And it's still only taking place any type of fusion is only taking place relatively close to the star's heart, because that's where you have high enough temperatures for all this to be happening. The surface temperature of the star might still only be a mere 4,000 or 5,000 Kelvin. So these series of nested shells is a really important concept, because all of this is all taking place at the same time. And what ultimately builds up in the very heart of the star is something that maybe the highest mass star could do something with. But even if it could, even if the star was at high enough temperatures to turn iron into something heavier, that's not going to get the star anywhere, because iron turns out to be this low point in energy output in fusion. So something really weird happens when you go through fusion reactions. While the temperature required to undergo fusion gets higher and higher and higher and higher, the amount of energy produced from fusion decreases. The most abundant reaction is turning hydrogen into helium. That produces the most energy. That's the most stabilizing process for a star. Then turning helium into carbon, carbon into neon, and so on down the line releases less and less and less energy, until finally you get to this bottomless pit of iron. Processes, fusion reactions involving iron and fission reactions involving iron just don't produce too much energy. That's kind of the low point on the graph as far as energy production. And if you're not producing enough energy, you can't combat the internal collapse of gravity. So even though fusion might even be taking place, it's just not enough to keep the star going, and the star dies in a spectacular death throw. Iron builds up, the star can't do anything with the iron, and even if it could, it wouldn't produce enough energy, and so the star explodes. And that single event is far, far brighter than any other point in the star's overall lifespan. In fact, it gives us this peak brightness to compare other events to. And we've seen these things happening throughout history. Obviously, this isn't the one that's pictured here on the slide, but as far back in history as 1054 AD, the Chinese astronomers were witnessing the birth of the Crab Nebula. They didn't know it at the time. They saw a supernova. They saw the death throes of a high-mass star. They saw this incredibly bright flash of light out there in space. So it only lasts for a short period of time, but it's incredibly energetic. Individual atoms are ripped to shreds, gravity crushing those particles inward, the outwards explosion of the star spilling all of the rest of the stuff, the hydrogen and helium, out into space to create a nebula that might be capable of producing hundreds of low-mass stars in its wake. So this supernova explosion leaves a remnant, and that remnant from 1054 AD created the Crab Nebula, which is probably one of the most widely photographed and famous of these supernova remnants that are out there today. I've got a picture in an upcoming slide here. The important thing as far as getting us the rest of the way down the periodic table is this is the final piece of the puzzle. Everything else on the periodic table, gold, uranium, lead, all of these relatively rare elements were created not in the normal pulse of the star, the normal process of fusion, but in the death throes of the star, in an event that might have lasted seconds. Now, what happens in order to form all of these heavier elements here is that the process of undergoing this supernova explosion rips apart individual atoms. So you're just left with protons, electrons, and neutrons to come back together in weird ways. You might have more neutrons than you have protons. You can create really weird elements. And a lot of the heavy elements on the periodic table are some of these weird elements. Now, that doesn't include what happens to the core of the star. The equivalent bones left behind in a high-mass star to a low-mass star are either a neutron star or a black hole in the dense interior where the core of that star used to be. So a white dwarf is an object that's held up by whole atoms by something called electron degeneracy pressure. A neutron star is being held up by not whole atoms, but only the densest part of the atom, only the protons and neutrons left behind in its very, very center. So at the heart of the Crab Nebula, whose birth was witnessed in 1054 AD by those Chinese astronomers in that amazing supernova event, at the very heart of this object, you have a remnant from that supernova in the form of what happened to that deep core. So either a neutron star forms, which is where you take all of these heaviest parts of the atom, the neutron and maybe some protons as well, and you crush them together as much as they can be crushed together, and you make a very small but incredibly massive object. Or gravity continues to crush down this material until it's nothing at all. It takes up no space in space. It takes up no room, but it has all of the mass of a high mass star. That's a black hole. So I'm going to leave that as something that we're going to figure out a little bit later. What lies at the heart of the Crab Nebula? Is it a neutron star or a black hole? First, I wanted to talk about this process of forming either one of these, either a neutron star or a black hole. With the kind of chaos that you get in the death throes of the star, in that supernova event, you rip apart all the individual atoms and you're just left with the pieces that make up those atoms. And the three primary interatomic particles are protons, electrons, and neutrons. One of the cool things that can happen is that protons and electrons can come together and neutralize each other. So the electron comes into the proton and decreases its charge from positive to something that's neutrally charged. So you can create neutrons. You can also create these things, these antimatter particles called neutrinos in the event, and it allows us to kind of keep tabs on how fast this is taking place. So mainly what you get is a whole bunch of neutrons that all slam down to the very, very core at once. And if the neutrons are not further crushed by gravity, if you just pack those neutrons together as close as they possibly can be, then you get something that makes sense in terms of where the name comes from. If it's just made up of primarily neutrons, it's a neutron star. If you crush those neutrons together so that multiple particles are taking up the same place in space, in fact, billions and billions of neutrons are all packed together and taking up the same place, then you create this object that it gets called a black hole, because it has this amazing, amazing gravity that not even light can escape. So we'll talk about these individually. First, let's start with the neutron star. That's weird enough. Neutron stars are even though they're not as weird as black holes, they're still absolutely incomparable to anything going on the Earth's surface. Now, the question of whether or not you end up with a neutron star or a black hole goes down to this question of what's happening with degeneracy pressure, and specifically neutron degeneracy pressure. At the end of the last episode, I played this little clip where Carl Sagan was talking about what holds up all these stellar remnants. And what he told you was that nuclear forces are what holds up a neutron star. So what this means is that individual neutrons are packed together as close as they possibly can be. And if you exceed that capacity, then you create a black hole in its place. So degeneracy pressure is basically a question of how much you can pack material inwards. And I always like to, because I traditionally teach this in a classroom full of students, I usually like to use the analogy of a classroom's capacity as being sort of the equivalent of the neutron degeneracy pressure. If you reach that capacity, but don't exceed that capacity for neutron degeneracy pressure, then you've packed together the neutrons as close together as humanly possible. That would be like in a classroom that has the capacity to seat 90 students. If every single student were each occupying their own chair, if I had 90 students in a classroom with 90 seats, that's the capacity of that classroom. Neutron degeneracy pressure, if each one of those students is equivalent to a neutron, is not exceeded, but that capacity is met. So that would be kind of similar to the conditions that allow for a neutron star to form. You have those neutrons packed together as closely as possible, but you don't exceed that capacity. Now imagine in the same analogy if I took the entire population of Earth, every single person who has ever lived on the surface of the Earth, and I packed them together in one desk in that classroom. That really shouldn't be possible. And according to the basic laws of physics, it's not possible. You can't have two people sitting in the same classroom seat. You can't have two particles existing in the same place. But the math would suggest, and observations of the universe would suggest, that this does actually happen. You can exceed neutron degeneracy pressure, and under those conditions, if two or more neutrons are existing in exactly the same place in space, then you have gravity crushing even beyond neutron degeneracy pressure and creating what's called a black hole. So the basic question to go back to here, just to kind of make this a little bit easier to follow, is neutron degeneracy pressure exceeded? If the capacity is met but it isn't exceeded, if your answer is no, then a neutron star is formed. If it is exceeded and your answer is yes, then a black hole is formed. And that typically requires an initial mass all collapsing together of at least 3 times the mass of the sun. So something like our sun is not capable, at least it's thought of, forming a black hole or even a neutron star. So let's start with a neutron star, because even that is going to be essentially an invisible object in space that contains most of the mass of the star from whence it came. This picture on the left here of a neutron star is not taken in the visible light spectrum, because in the visible light spectrum, all you see would be just gas surrounding this object, and you wouldn't really see the object itself at all. Those dim colors in that picture are actually false colors given to an X-ray image. And in X-ray, we can actually see or begin to be able to detect the surface of a neutron star. So this neutron star is the result of, again, just the core of that high mass star collapsing in on itself, but not to the point where two particles are taking up the same place. You've just basically taken just the heavy components of the atom, not whole atoms, like in the case of a white dwarf, but just the heavy neutrons themselves, and compacted them together as closely as they can be compacted. These neutron stars are also sometimes referred to as being pulsars, an idea that we'll get back to in just a minute when I talk about the discovery of these objects. But first, let me kind of talk about how big these objects can be, because the remnant of something like our sun could be the size of Earth when you account for the compaction down to the white dwarf limit, to electron degeneracy pressure. So something the size of our sun can be compacted down to the size of our planet, making it relatively small but very dense. A core of a high mass star is even bigger initially, but it can be collapsed down to something the size of a small city. So imagine a star that was initially 2 or even possibly 3 times the mass of our sun being collapsed down to something the size of the city of Hammond or Covington. It would have the same overall diameter. This is an incredibly small object in space. And so because it's not producing any light, and because it's so tiny, we really almost can't see it directly. We can see its result on other wavelengths of light. Neutron stars were first detected and referred to as pulsars by a scientist in the early part of the 20th century named Jacqueline Bell. She was able to image these pulses of radio waves coming from a particular region in space. So something was creating these radio waves, but allowing them to pulse. And so they got the name pulsars. And these were just weird astronomical objects for a long period of time before somebody actually speculated on what could be creating those pulsing radio waves. So these pulse at many, many hundreds of times per second. And what they actually are rapidly rotating neutron stars. So they're spinning around really, really, really fast and emitting these radio waves outside of their magnetic field. In order to even have a magnetic field, they have to be at least slightly charged. So they're probably slightly positively charged. So they're not entirely made of neutrons. There might be some protons in there too. They are spinning around a rotationary axis and creating magnetic field that's offset from that rotationary axis. And outside of that magnetic field, that's where they're creating a constant radio wave. Now, the fact that they are rotating while they're creating that constant radio wave is what gives the illusion that they're actually pulsing. So they're not creating this intermittent amount of radio waves. They're spinning while they're creating a constant amount of radio waves, so that allows them, when they spin around and point towards us again, to look as though they're actually pulsing these radio waves while they're really just rotating. So the effect is very similar to a lighthouse. If a lighthouse is producing a constant beam of light in one direction, but it's spinning, then whenever it spins back to you, you see a little blip on that light. And the speed in which it's rotating is equivalent to the number of times you see that little blip of light in some given amount of time, like in seconds. Because these are rapidly spinning neutron stars emitting these radio waves, we can pick up on these radio waves many, many, many times a second. And it turns out that in the dense cores of these leftover supernova remnants, we can pick up on these pulsing radio waves. So to go back to the original question of what is at the center of the Crab Nebula, the event that started in 1054 AD with that big supernova event, it's actually a neutron star. That's what happened to the core of that star that was left behind. Its atoms were ripped to shreds, neutrons and some protons were slammed together to the very center to create this neutron star that continues to give this illusion that it's pulsing radio waves, when in actuality it's a spinning neutron star. All right, now that's weird enough. A teaspoon of the material that makes up a neutron star would be enough to crush a building on Earth. That's how incredibly dense this material is and how incredibly strange it is. But these stellar remnants of high-mass stars get even weirder, even more bizarre. Such a thing called a black hole is one of possible outcome in the death throes of a high-mass star. So instead of whole neutrons, just the massive part of an individual atom being the thing that's actually keeping this object up, even gravity is crushing together even those objects, so that you can have billions and billions and billions of times the mass of the sun in one point in space. That's why Carl Sagan said that a black hole is almost like gravity has crushed matter into nothingness. It still contains that individual little pixel in space, or that spot in space, that atom in space. Any unit of volume is kind of not important at this point. But whatever space that object is actually taking up, it is the sum of an untold amount of mass, and that mass can actually increase over time. So the reason why it's called a black hole, first off, is because while these are some of the most interesting and the weirdest physical objects out there in the universe, it's an object that doesn't produce any wavelength of light. And because its gravity is so great that not even light can escape it, light traveling at 300,000 kilometers per second, then it stays dark to us. It's a black hole. It's also a black hole in that it does really weird things to the fabric of space and time, to the curvature of space and time. And that's something that we'll close with a little bit later on. So only under certain conditions, if you have a massive enough star and if the core of that star slams together fast enough, can you have gravity actually overtaking both electron degeneracy pressure and then neutron degeneracy pressure to allow all of these particles to come to rest in the same place in space. What you've ultimately created here by exceeding neutron degeneracy pressure is a singularity. The singularity is the point at the very, very center, at the very core of what we're calling the black hole. So the core of the star is going to collapse inwards, collapse inwards. One thing that precedes the onset of the formation of the black hole are, again, these jets of matter being ejected out of the rotationary axis, and then nothing. Just a dark spot in space. So gravity's crushing everything together to take up a single point in space. And this is one of these things that's incredibly difficult to actually picture. First of all, because, I tried to come up with some kind of graphic to show you for what a singularity looks like, and it would just be nothing. It would be at best a single point on this slide. But even that isn't entirely representative of just how small the singularity is. Smaller than an atom, smaller than a neutron. You've essentially crushed matter into nothingness. But that nothingness, that single point, contains an incredible amount of mass still. So it still has an effect on all of the other objects around it. Objects can still rotate around a black hole, for instance, but they're rotating around seemingly nothingness. Now, what ultimately happens here is a lot of weird relationships between how fast light travels and how fast gravity is crushing things inwards. And so this is as close as I can come to actually giving you sort of a graphic of what's going on in a black hole. Almost everything that's actually pictured here on this slide is not the black hole itself, but the effect of the black hole on all of the space around it. First off, because it's so incredibly small and massive, you have an accretionary disk, and that's the first thing that shows up in this picture, is gas, even entire stars, entire solar systems orbiting around something like a black hole extremely rapidly. And so this accretionary disk could allow for an object to orbit around it harmlessly, but what more often will happen is that collisions between particles cause a change in trajectory and material starts to be accreted into and become part of the black hole. At the very, very, very center of this picture, underneath the jets inside the accretionary disk, is the black hole itself. And so while up into the point of no return, you can still detect the light from all of this accretionary matter, right at the edge of the black hole is when light can no longer escape it anymore. And that point of no return for light is called the event horizon. Its distance from the singularity is determined by the mass of the singularity. If it's as small as it could possibly be, which is only 3 times the mass of the sun, then that black hole might be the size of the city of Hammond, the event horizon of that black hole, that is, the point of no return, in a sense. So the event horizon is essentially just the point away from the singularity where the escape velocity of that object, that very, very small but massive object, is equal to the speed of light. The escape velocity of Earth, for instance, as a matter of comparison, is a mere 11.2 kilometers per second. The escape velocity, even at this distance away from the singularity, is equal to 300,000 kilometers per second. So you have to be traveling faster than the speed of light to be able to escape this point, and nothing in the universe travels faster than the speed of light. That's an absolute cosmic speed limit that's been laid down. Nothing can travel faster than the speed of light, so nothing then can escape a black hole, including light. Now, within the escape horizon, then within the event horizon, the escape velocity only increases and increases and increases as you get to that singularity. If you look at the formula for escape velocity, it's dependent upon mass, which has a positive relationship with the escape velocity, and radius, which has a negative relationship. The smaller the object is and the more massive it is, the higher the escape velocity, which is why these things have such an incredibly high escape velocity, even higher at a certain point than the speed of light. So light can't travel away from it, so that's the point of no return. That's the point when the object is a black hole, essentially. Now, what's actually happening here, according to a theory that Einstein put together in 1916, is that any really, really large object in space is having an effect on gravity by warping the fabric of space and time. By warping the fabric of space and time, this allows for other objects to always be sort of falling into that more massive object. So, for instance, the reason why we continue to orbit around the sun is because we're falling down into that pit that the sun makes in the fabric of space and time. This is part of Einstein's general theory of relativity. So if you carry on that metaphor, that any object that is very, very massive is creating this warpature, this dip in the fabric of space and time, then that makes a black hole, and especially the singularity at the center of that black hole, like a bottomless pit in space and time. So while a star might only slightly warp the fabric of space and time, a more dense, smaller version of the star, like the white dwarf, for instance, would have a greater effect on the warpature of space and time. That's the stellar remnant of a low-mass star. A neutron star, being even smaller and having an even higher mass, would cause a greater warpature. And then finally, a black hole would have basically an infinite warpature in the fabric of space and time. Now, if any of this sounds really, really incredible, if it sounds like something that you can't believe or we can't prove, you only have to go back to the work that was done just a little over a year ago, even here in Louisiana at the LIGO facility, to prove this idea. 100 years after Einstein originally came up with the idea, LIGO proved this pretty much. And they proved this by detecting these things called gravitational waves. Now, this is where we sort of reach the end of my ability as a mere geologist to start to really kind of keep up with this anymore. So I found a really cool clip for you where a physicist, an astrophysicist named Brian Greene describes the LIGO accomplishment, and he describes, again, Einstein's general theory of relativity and this warpature in the fabric of space and time, and how important this particular discovery of these gravitational waves really was. So I'll let you enjoy this little clip here.
Now, what is a gravitational wave, and why does it sort of change everything?
So a gravitational wave is actually a ripple in the fabric of space, right? We know you throw a pebble into a pond, the water ripples, right? Mm-hmm. Now this is a ripple, but not with water. It's in space itself.
You are blowing my mind again. So what are we looking at here?
Well, this is Einstein's general relativity, which he discovered in 1915, a year earlier. And the key idea here is that he found that gravity comes from warps and curves in the fabric of space. So the sun warps the space and keeps the Earth in orbit. It kind of rolls along a valley.
Kind of like a bowling ball on a trampoline.
Trampoline, exactly right. And what happened is, this is 1915, he doesn't just stop. He keeps going, and a year later, he realizes that if space is like a trampoline, then imagine kids running around on a trampoline. They're going to send ripples on the surface. So he says the same should be true of the fabric of space. If you've got two rapidly orbiting stars, neutron stars or black holes, his math predicts that they will generate a steady march of ripples in the fabric of space. Those are gravitational waves that he predicted mathematically.
And now they have been detected.
Yeah.
What happened that allowed us to do that?
Yeah, so his math also shows, if we go on from here to the next sequence, his math shows that as a gravitational wave ripples by anything, it will stretch it and compress it. You see it happening
like
to the Earth right here.
So literally, because we're part of the fabric of space-time, you and me and the Earth is stretching and compressing along with the rippling of space-time.
That's exactly right. Now, the one thing is, this is exaggerated a little bit.
I hope so. I hope so.
The ripples would actually cause the Earth to stretch and compress by less than an atomic diameter.
Well, how do you measure that?
How do you measure that?
Yes, that's what I said.
Yeah. That's what people, thousands of scientists have been working on for 40, 50 years. This amazing team of researchers LIGO, it's called, Laser Interferometer Gravitational Wave Observatory. Just 2 weeks ago, they announced the first detection of these gravitational waves using a spectacular piece of equipment. There's actually two of them, one in Louisiana, the other in Washington State.
So one of the biggest reasons why I wanted to show you this is world-class physics going on. This is an amazing achievement, and not a whole lot of people can believe this came out of Livingston Parish, Louisiana, out of the LIGO facility. So I can't begin to tell you how excited I was for them and what a big deal this was. So this should sort of round out our whole discussion of not just black holes, but stars in general. Now, stars are just going to be one of many, many objects that are making up galaxies. That's going to be our next lecture, lecture 23. And beyond galaxies, we'll look at the history and future of the universe in the very, very last lecture in this class, lecture 24. So two even more exciting subjects coming up in the future. Until then, keep looking up.